All right, thanks the organizers for inviting me. It's been really fun being here this week. I hadn't been to Europe since before COVID, so it was nice seeing people again. And yeah, I'll tell you a little bit about work which is done with various combinations of the people down here. I want to especially highlight, Melissa, who was here a few weeks ago, and Tewook, who are both postdocs and will be applying this season. So, if you're hiring, take a look. And also Will Svetko, who is an undergrad at Utah, who started working with me and Melissa on some of the things I'll present towards the end of the talk. And I come from the particle physics side, and I have a somewhat some impressionistic view of how a lot of the cosmological analyses are done, and it gives me a lot of fear, and some of it was confirmed by Marco's discussion yesterday. That every time you want to do a cosmological analysis, essentially you take every single ingredient, you take a few information from inflation, and then you need every single aspect of lambda CDM and gravity, and then you have to run some complicated simulation before you can say anything about your model. And that's much more complicated than a lot of times when you're thinking about a more laboratory experiment for particle physics, where you can isolate the physics into some small amount of ingredients, and you only need to calculate using a small subsection of your theory. So if anything else is modified, you don't care, because if you care about how many dark matter particles are interacting with xenon atoms, you don't really care about the neutrino masses or anything like that, right? So it would be nice if there's some way to simplify cosmology. I think it would make this back and forth between particle physics and cosmology a little bit simpler. But okay, that's just, my simplified opinion. But we're here to talk about new physics using galaxy clusters. And my impression a lot of times when I go to a meeting that has more cosmologists than particle physicists, is that when you think about new physics, the majority of people want to talk about either, something that is changing inflation, something that's changing lambda in lambda CDM, and something that's changing gravity. Right, and that's fine, but I think if you would go to a meeting with particle physicists, your prior would be totally different. It's very hard to model build in almost any of these directions, and it's fairly simple to model build the CDM. And lambda CDM has more letters in CDM than in lambda. So but no. And if your analysis is very complicated and requires you doing all this difficult work, you should think about your theory priors maybe a little bit before you decide on what is the best use of your time. And, of course, I'll do it for my time. You can do whatever you want for your own time. And what I want to do today is tell you a little bit about different scenarios in which we modify something in the CDM sector, which makes it no longer C, right? Okay, no longer code. And maybe it will become more fashionable if I call it lambda IDM. It will catch on. I don't know. For interacting, okay. So what kinds of if I'm sticking to sort of cosmological observables in which maybe I can have some sort of perturbative control, because it's hard to do things if you have to do simulations for BSM models. It will use infinite computer power. It will never do it. So let me try to stick to scales that are more or less close to perturbative control. So if I want to affect modes that are below k of maybe 1 inverse megaparsec, and but it's something that is interacting with dark matter, I often will need a light mediator or a light particle to be around. And light compared to kV to EV scales, it could be massless. And therefore, if I'm in this business of thinking about an interacting dark sector that has useful implications for cosmology, I'm sort of already stuck with a picture with has 2 particles. Okay, you might not like it, but it is what you're doing if you're talking about interacting dark matter. Dark matter with some interaction that you have a hope of seeing in cosmology. And some of you might object and say that maybe it's distasteful. Okay. And but it's relatively simple models. We can write a Lagrangian for them. They can have interesting experimental implications. So I'll continue, okay, despite objections. And I hope you'll still invite me to GGI later. And so let's, there are kind of different classes of models in which dark matter can have interactions. And I think there's a separate class, which until recently people had made very little attempts at tackling. and it's very interesting on its own. It's in which dark matter can have, coherent interactions over long wavelengths. Essentially, you can have, and essentially it means that all of the dark matter particles would have the same kind of charge, so that, you can interact with the full body of dark matter. And then in that case, you're sourcing a potential out of that full body of dark matter, and it's more something like gravity. Or if you could have very objects with very, very large charge, so you get in that case you're sensitive to incredibly small cross sections, because you can just take a ton of dark matter particles to compensate for this small coupling. And this is I mean, I've never worked on this, but many of the people organizing this and visiting here have recently thought a lot about it. So if you I guess they're all sitting here in front, so just go bug them. But I thought this is, I think, a very interesting direction, and something that has been widely underexplored. And I was told to do a little bit of an overview, so I wanted to talk first mention something that's not something I've worked on, but I know very little about this except the authors. Then but most of the models you're going to write down, right? Okay, so if you want to have this thing where all of dark matter has the same charge, you're kind of stuck with a very few kinds of models that can do that, and that are well defined. So the majority of models in which dark matter is interacting, the phenomenology is dominated by interparticle scattering. So essentially two processes. So not coherent over large collections of dark matter particles, but really you care about each individual dark matter particle, how it's interacting with other individual dark matter particles. In that case, this is characterized by some sort of hard scattering between the two. And then the first, if I'm taking inspiration from what I just said before, the first thing you might consider is, dark matter interacting with dark matter itself, right? And if you do that, and you have only one kind of dark matter species, then it turns out that at least in linear perturbation theory, that doesn't do anything to cosmology, because it doesn't really change the momentum of the fluid. The dark matter is the fluid. If it exchanges momentum with itself, it continues with the same momenta. And as far as I can tell, it doesn't have any effect in any perturbative scenario. But it does have very interesting signatures once you go to sort of more nonlinear, very nonlinear scale. So people have spent a lot of time thinking about how that might affect galactic dynamics, how to maybe solve the core versus cusp problem, the diversity problem. So there's lots of interesting work on this, which I guess I failed to cite. I mean, I was planning to do it, but I forgot. But I know the group in Irvine, Oren Sloan in Tel Aviv, a bunch of people have really spent a lot of time in the past 5 years or so, and I invite you to go look at their work. I've never worked on it. But so I mean, I'm saying sort of a general statement that if the interaction is between dark matter and itself, that at linear perturbation theory, and as far as I can tell, even if I just try to put in some kernel, I don't think it does anything to cosmology in some perturbative regime. Doesn't do anything to the dark matter over densities. Although I'm not sure. Yeah, yeah. Sorry, but a fluid more, my long range in your case, that every dark matter has the same charge, then yes. But if if each patch is more or less charge neutral, then no. Yeah, yeah. That's true. Yeah, yeah. No, just from the bounds, but yeah, yeah, that's true. So okay, but but I already told you from the beginning that we're stuck with two species, right? So we have dark matter and we have the mediator, because we want to have something interesting happening. So we can also just talk about what happens for cosmology when those two species exchange momenta, right? So about the interactions of dark matter with the mediator itself. And in that case, you get to this class, which is what I'll spend most of the talk discussing, of models in which dark matter interact with some form of relativistic species, what I'm going to call dark radiation, which can be the mediator, or if you can become more creative, and can be other stuff as well. But it doesn't matter too much. What really matters is once you're in this particle to particle scattering process, what you care about is the rate at which the two fluids are exchanging momentum, which you can easily calculate given any model. And often it will just be a simple power law of the temperature. right? I mean, there are no scales in the problem. Once the dark matter is sufficiently heavy and the mediator is sufficiently light, the only scale is the temperature. And so this rate is going to depend on the temperature to some power. And for most powers you can choose here, as you go to lower redshifts, the cross section will start going down because it's a large power of the temperature. And will be that at early universe the interactions were very big, at late universe the interactions are very small, and that will produce a feature in the power spectrum because essentially those modes here suffer lots of pressure from being interacting with this radiation. The modes here don't see anything, and therefore they just behave like cold dark matter. And you get things that sort of, if you just take the transfer function, I think this is really ratio of transfer functions, but I now don't remember. And, it just, at very small, at very large scale, so very small k, nothing's happening because you're in this regime, right? And at very large k, which entered the horizon when the interactions were very important, you get large suppressions to the scale power spectrum. And you can put very strong bounds, where this cutoff is at order 10 inverse megaparsec or so way beyond what we can do using just perturbative calculations. This was done, I think, using studying populations of dwarf galaxies, but you can also, say things using Lyman alpha, or I guess Eli was also talking about something using intensity mapping. So they're different regimes, but essentially you're pushed to the case when this is happening very, very early on. And so also probably not the best for if you're looking for new physics in galaxy surveys. That's also not what you want to be doing. Except there's one exception to this rule, which we kind of figured out a while ago, and was sort of interesting because we did not set out to go look for this. It was mostly trying to understand some of the implications in cosmology with Martin and Julian and Manuel, and we figured out that the model that we happened to be considering had this scaling when the scattering rate goes as the temperature squared. And in that case, the cross section is a constant, so it can be even small, so don't completely erase structure, but it's a constant over a long time. So it can be a small effect, but it acts over long cosmological scales, and that leads to a much smoother suppression that sort of goes as a log in k instead of being just it's essentially like almost exponentially suppressed. And this, gave us a nice template of something that maybe now you can actually go and look for in large scale structure. And I know that Enrique and Matias have actually done some very nice work in using the EFT of large scale structure to look for that. And later on, so this turn off here for us was happening more or less when you switch to matter radiation equality, at which point Hubble starts scaling less fast with temperature. And at that point, this interaction would just become less and less important. So this was happening close to modes that enter near matter radiation equality. But later on, inspired by doing some H0 work, Melissa, Martin, Danielle, and others, they kind of build a slightly more complicated model where they could shift this feature around. So you'd still keep this log k scaling, but you could essentially move where it starts. And it was useful for some H0 model building. Very easy, massless mediator exchange. So T-channel massless, yeah. Okay, so that's one model, but we want to have a zoo of models so that we can maybe think about different search strategies. So now I'm going to introduce a third thing. Okay, and I don't have as good logic to tell you why you should introduce a third thing, except that it allows us to look for more signals. So maybe dark matter has two components, one that is cold and is boring, doesn't do anything, and then one that is interacting with this dark radiation. Once you have these two components, now you don't necessarily, as long as this interacting component is, order like 10% or less, it's harder to use this very short distances probes because the uncertainties are larger and the effects become much smaller if you only have 10% or less of dark matter. And at that point, you can have the strong interactions with the radiation, right? And so the cold dark matter would fall into gravitational potentials, while the interacting one would try to fall in, heat up the dark radiation, and get spelled out because of pressure. And that's more or less controlled by whenever the sound speeds start deviating from the relativistic species. So essentially when they're, effectively, besides the scattering rate, which I didn't include here, so if the scattering rate is sufficiently large, you're in some tightly coupled regime. And in that case, you're mostly, controlled by this ratio of how much energy density is in dark radiation versus how much energy density is in dark matter. And, in this case, even if the interactions are very, very strong, so you can have this tightly coupled fluid, you have dark matter having strong pressure support from dark radiation, but once the sound speed starts deviating significantly from one, those modes can still grow. So what you would find is modes that enter the horizon after you have more dark matter than you have dark radiation would just behave like cold dark matter. And the ones that enter the horizon earlier are highly suppressed. So you get now a step-like feature in the power spectrum. But there's sort of, two possibilities now. And I wanted to highlight this because I think this kind of comes back to this idea of whether we can have simple templates or not when we're looking for these kinds of models. So here I'm showing two different models, which we have, I guess I didn't create all of these names, but both of them at early times, so both have dark matter being tightly coupled to dark radiation at early times. One of them never decouples. So, just that rate is so large that the dark matter is this interacting component, which is a subcomponent of dark matter, is always interacting with dark radiation. And this is this dashed line, which is this partially acoustic dark matter. It was done by this folks here. While the other one, you have the interactions decoupling at around this redshift of decoupling here. And you see that at that time, I mean, this is maybe not the best representative because I put decoupling too close to matter radiation equality. I shouldn't have done that. But essentially from decoupling on, now the sound speed essentially is negligible instead of being just something that's decreasing slowly. And in that case, it can quickly catch up to the cold dark matter component. This is more like what baryons do. Okay, so baryons were not falling into gravitational potentials early on because of pressure support, but once they decouple from the photons, they very quickly catch up with the dark matter. While if you're always interacting, those modes never catch up. And the reason, I wanted to highlight this is because, we had those nice talks earlier. I didn't put their names, but they had some very nice talks about the relative, when you have two fluids, whether you have to care about, biases coming from the relative densities between the two fluids. You should just look at the talks from Tuesday, I believe, or Monday, Tuesday, that really discuss this. I think in this case, you really care about it. And and you have to model it correctly, while in this other case where it quickly catches up, like I think this relative mode is just a decaying mode and you don't have to care about it at all. I think maybe having two, kind of fairly extreme scenarios might allow you to sort of model what is the uncertainty in doing this kind of thing. Okay, so now you've probably found me guilty of model building. And if you were here for the panel discussion on Tuesday, you can be guilty of multiple things. And I didn't really understand from the panel if it was good or bad to be guilty of multiple things. I'll take it to be good, okay? So I confess I've also done some of this because I was trying to solve anomalies. So, and the good thing is that, if you're trying to achieve, if you have a goal, it restricts, narrows the number of models that you're looking at, right? So it forces you to focus on some more specific features. So, even if you don't believe the anomalies, it's usually a nice exercise into trying to, flex your brain on what kinds of signatures, given the constraints, can I really see? And the one I spent the most time thinking about was H0. And we had a very nice talk about Julian, so I'm not going to spend a lot of time discussing the motivations, but essentially, if you're really trying to solve H0, the most likely thing you're trying to do is you're trying to modify the sound horizon scale without compromising the fit to the CMB, right? So you have a model that allows you to modify the sound horizon without compromising the CMB. And so I'll try to see if this kind of dark matter, dark radiation models, if they can help. And in some sense they do. We'll see. It's an evolving story. But I'll take one more step. I'll take since I've taken dark matter and dark radiation to be self-interacting, I might as well take dark radiation to have self-interactions as well. And it turns out to help, so I'll keep it. So my model will have one component of dark matter, which will be a subcomponent interacting with dark radiation, and the dark radiation also has self couplings which are largish. And I think the main challenge when if that's what you're trying to do, and I think in the end it's what most of those models that try to solve H0 are really facing, is that there are really three scales. Trying to solve H0 is trying to change the sound horizon so that you can because once you change the sound horizon, the position of the peaks force you to also change the angular scale, and that's really why you get to change H0. But the third scale is essentially the width of the acoustic waves, right, which is more or less controlled by the diffusion of the photons when like close to recombination. And the problem is that the diffusion of the photons is a diffusive process, so it cares about the square root of the time. And so if you're trying to rescale all of your if you try to rescale all of the fundamental scales in the problem to try to surf on some sort of degenerate direction, this breaks that degeneracy and doesn't really let you scale everything up, because if you scale Hubble by some amount, you only scale the diffusion length by the square root of that amount, and that moves where the silk damping scale begins. And that tends, you're trying to make the sound horizon smaller, but you make you don't change the diffusion scale by as much, so you move the diffusion to lower L's. So you get more suppression on the CMB. And well, I guess I shouldn't say within lambda CDM, I should say within lambda CDM plus radiation models, you don't have enough freedom, right? I mean, the things you can try to change to compensate, let's say, and the thing to admit is that the lambda CDM is a very good fit to the CMB. So you don't want to spoil that. So if you're enhancing damping, you're probably spoiling that. So you need to try to compensate for it somehow. But you only have a few tools, right? I mean, and the one that does close to working is you try to crank up NS a little bit. You put in a little bit back, put more power at small scales by changing NS. But the problem is that it's a trade-off. I mean, NS is controlling this, the slope of the primordial power spectrum. So if I put more power at high L's, I'm putting less power at low L. So I can't fully win, right? I mean, I pay a penalty somewhere. I can also try to change the helium abundance, but that we have bounds on how much helium there is in the universe. I can change it enough to make this work, so I'll not consider changing helium. And so the problem with the traditional just dark radiation models is that they, just having an S is not enough. But if you could do something that is more L dependent, so that you now somehow differentiate between low L and high L, you can try to combine that with an S, and now you actually have more sculpting power. So since I'm guilty of signal building and anomaly chasing, I can try to sculpt my signal. In these types of dark interaction models, they can do that because they're changing the power spectrum in a K-dependent way. So the question is whether is this K-dependence useful? And so that's what it does to the power spectrum. This is what it does to the CMB, right? This is just residuals compared to the best fit to lambda CDM. And on the left is what happens if I change the amount of interacting dark matter. So maybe from 2% all the way to 10%, and you see that there's some wiggles, but it's primarily just creating an overall decrease in power at high L's, and a small bump at low L's. And then I can also change when the transition is happening. So I can move this plateau to higher and higher L's all the way to, I just can't see it anymore. This is, sorry, fixed. Yeah, fixing the angular size of the horizon. So I'm actually, yeah, this is actually a lie that this is the best. It's not quite the residual to lambda CDM. It's the residual to setting the fraction to 0. So that I isolate just the effect of having the interacting dark matter. So yeah, that's right. So this label is misleading. It's not lambda CDM. It is just in that case, it's just a radiation model, right? With the dark matter being non-interacting. Sorry, that's really what the residual is. And so we studied, I mean, we actually looked first at a very specific example. It worked out very well. And then we were curious if we had just lucked out and, found the best possible model, or if it was a more generic feature of interacting dark matter with dark radiation. It's something that we're doing now, essentially kind of parametrizing this in a more generic way. And we're looking at essentially 3 examples. One in which, this scattering rate scales as n to the 4th. And, it's a little annoying that the n goes as 2 plus n, but it is the standard in the literature from, I guess, the ethos paper. So I'm just following their lead. And this is more like if dark matter interacts, if dark matter maybe had a U1 charge and it's interacting like Compton scattering. So this is, it gives you this T to the fourth scaling. So very much like the electron scattering with photons. N equals T to the 6 is more what you would get if you have a dimension 6 operator, right? A 4 fermion operator, for example, like the weak interactions, or if you have, if you integrate out a heavy mediator, you would get something that scales like this. And then N equals 0 is sort of like the thing we discussed before, that it scales the same as Hubble, but then it would never decouple. So we put in, a decoupling that's coming from some sort of freeze-out process. Here we're just modeling it in a very agnostic way, but there's some model realizations of approximate that gives you approximately that. So we're just trying to capture the main physics of this. And so effectively, this model only has 3 parameters, extra parameters that control it. It's the amount of dark radiation, the amount of interacting dark matter, and when did they decouple, right? So you can essentially map out the parameter space into those 3, and those are the only 3 things that will affect the cosmology. And you can do fits. So if you do fits of these 3 models, we did this, started this earlier this year. So we did with Planck, BOSS, and Pantheon Plus, and so not putting the prior on H naught. This N equals 0 model allows you to go to an effective at 95% of almost 1. And it allows you to go to H naughts of 72-ish at 95% level. So that's much better than we were expecting, I must say. And that gives us a little bit of hope that maybe this is really some interesting direction to explore. Then if you put in the shoes prior, you just put the Adam Rees measurement, the H naught measurement from the shoes collaboration, then it really has a non-zero and effective. And in particular, the N equals 0 model can just nail H naught at exactly 73, because there's sufficient degeneracy now that you can essentially just move that to be exactly at the central value of shoes. And and you get a chi-squared compared to lambda. I mean, it's a little bit misleading because this is feeding both lambda CDM and those interacting models to the data that includes shoes. So, lambda CDM has a little bit of a penalty, but you get a chi-square that's better by about 35. And, without penalizing your chi-square to the CMB data. I mean, you don't make it better. I think it's kind of hard to make the CMB fit much better, but it doesn't seem to penalize it in any way. This is BOSS BAO. Good, yeah. It is, yes. It's, good. So, and this is, it's in preparation, coming out, I think, sometime later this month. But no, what about the power spectrum? Okay, so I introduced this because we are in this galaxy, trying to look for new physics in galaxies. So I should talk about the power spectrum and not the CMB. And so this is if I take the power spectrum of lambda CDM fit to the, to just Planck plus BOSS and BOSS BAO, not BOSS full shape. And I compare the best fit of our models to this data set here, so including shoes. So, if I try to push the model as much as possible in the direction that is away from lambda CDM to solve the shoes, to solve the issue with H naught, we get, that the power spectrum is more or less, fairly flat with, order, 2% oscillations, okay? Which, you might ask, okay, I mean, this is more flat, when I showed you, it was a step-like feature, but of course, you'd adjust every single other parameter, it no longer looks like a step, but the wiggles remain. And then what do we get if we now do a fit doing full shape with BOSS? So we did it with PyBird. And, we still get, a reasonable fit, but it's clearly not going in the right direction. Okay, so the chi-squared, instead of being 35, is now more like 15. And you can also see that, H naught is getting pulled back towards the smaller value. So it's, not so good. But, it is what it is. I will try to be, okay, maybe before I'm positive. The error bars also change. So in the thing that, and maybe here's the other place where I, want to maybe get input from the audience. I find it kind of difficult to fully interpret the results when I'm doing this analysis with full shape, because I didn't show you, but if I do, so this is including the shoes prior, right? I mean, that's why it's still preference for non-negligible and effective. And you see the fit to the CMB is reasonably comparable, even though I'm doing much better with H naught. But if I do the same fit without shoes, then it doesn't want an effective at all. Like a bit, it constrains me, pulls me all the way back. It's a very dramatic shift, and I don't know if it's some sort of prior volume. It's very hard to understand what's going on. Yeah, so that's why I'm a little worried that because full shape has more parameters and there's the degenerate direction, but if I go towards zero and effective, then I lose sensitivity to all the other parameters. So I just don't know if there's some weird volume effect going on. Yeah, so yeah, it's like between equality and 10 to the minus and then 10 to the 4-ish. It's like it's in that ballpark between a few thousand and then 10, like 10 15,000. It's in that ballpark. Yeah, you kind of want to be affecting case of order 0.1, right? So that's where you put yourself. um yeah. Yeah, I mean, this is I mean, so I must also say that somehow this I mean, this n equals zero model did better than we were expecting. um but okay, but clearly, I don't know, whenever I would want, that I put more data and I get more evidence for my model and not less evidence for my model. So, it makes me more pessimistic. But let me be a glass half full person. Okay, so seems like we arrived at a great era, right? We have sensitivity to order percent level effects on the matter power spectrum, which is, what this meeting is about. And in particular, we have these features. We have wiggles. So I unashamedly stole the joke from Sam earlier. And, so we should really think about how to do these things. And, with Marco and Diego, we're starting to try to figure out, how well can we go after such, relatively striking features, right, which seem to survive even when I model. I mean, it's very hard for any of the other parameters to create wiggles. So, I think, and it's not dissipative. It depends on what it couples to dark. It is, but you can make it, not that dissipative. I mean, depends on the model. Then you have to figure out what the model is, but uh, different variations are more or less dissipative. And we're happy to talk about. Yeah. One of the realizations is definitely on the non-dissipative side. Yeah. The one that's closer to actually that. It's not an ugly realization it's not a beautiful realization of that, but it is a realization of that regime. Yeah. And the other thing I wanted to highlight is that, and I think that's where, having people from two communities talking is that, maybe you think that you can only get these oscillatory features from inflation. And I'm just saying you can also do it from CDM, and it's much easier to do it with CDM. So no, I think these oscillatory features are motivated by more than one thing. Now, I'm not living in some isolation vacuum. I saw Arminia's talk, and I've been deeply concerned about what ACT is going to do to our models, because if I take our best fit and I just compare the residuals, right, with lambda CDM, I see that the residuals become, more and more pronounced at large L's. And therefore, if our model is true, I would expect that ACT would start seeing it, because, they have much better sensitivity at high L. So, are we, should I be, getting ready to celebrate? And and unfortunately, no. So Melissa and I and Will have been investigating this. We're still like trying to understand. I think there's still we're still plagued with some annoying prior volume issues if we don't put in the shoes prior. I mean, we have this very non-Gaussian results for ineffective. So I don't know how to interpret our results for ineffective yet. But but even if I put in the shoes prior, that before it would just you push me all the way to large H naught, now I'm getting pulled back by quite a bit. So it does seem like ACT does not like the suppression at high L's, which you could have interpreted from just from their ineffective results. we were sort of hopeful that because we have this feature, maybe we could bypass it, but it doesn't seem like this is going to happen. So not looking so promising. But I think, as I said, I think the tensions are useful to kind of make you focus on specific features and force you to care maybe enough to really work out a bunch of details. But I don't think that makes, that would should make us stop considering interacting dark sector models, especially because we know nothing about dark matter and we're just getting, this very, very good quality data that allows us to go after things that we could never do before, right? So, I mean, there's no way you could have done percent level, small changes in the power spectrum 10 years ago and say anything. And it seems like we're there. So yeah, with that, I just want to give my summary. I think dark matter, dark radiation models, you can build nice models, you can build ugly models, but they give you a nice flexibility of getting signals at different scales and that are tailored for different experiments. So, they're a very good tool for doing signal building. But they are well defined. We can write a Lagrangian, we can calculate everything. So I think they're a nice, very nice kind of playground to try to look for interesting signatures. They definitely change the bounds on n effective and also shift other cosmological parameters. So they give you some sense in which how well are those parameters really constrained if you modify the physics by a little bit, right? I mean, we often frame n effective as a very robust model independent way that you can just put bounds on, many, many different models. But at least before ACT, you see that if we modify that dark radiation by a little bit, we could essentially change the bounds by, factors of 3 or 4. So, you should really keep always that in mind that nothing is really all that model independent, which should not stop us from trying to do model independent, claims, but we should have that in the back of our minds because, when we wrote some of these papers and we get referee reports, like, no, how come you can have an effective of 0.6? So that you should be ruled out. It's like, no, we're doing the fit. It seems like there's a miscommunication of what people are doing. Yeah, we got to the point that we're sensitive to this, order percent features. We should really figure out what can we do with it. I think there's lots that we can do. Yeah, ACT is not good for dark sector models. But as I said, I think there's still a useful framework to just explore the data in a maybe more open-minded way, and it's all well-defined, all calculable. So I think that's maybe a good framework. And with that, I want to advertise that next summer we're organizing something with a similar spirit, maybe a little bit more particle physics centric, but but with this idea of also bringing particle physics and cosmologists together to figure out, what can we, how can the two communities have synergistic, activities and really create maybe new both like benefit from the data, but also maybe try to figure out new targets that can motivate new analysis or new experiments. Thank you. So we unclear. We're trying to play with it now, but we haven't gone. I mean, depends on. I mean, we can move that K based on where we put the decoupling, right? So the question is like, yeah, at K of 1, it seems tough. I mean, also based on like, I mean, I guess Sam's talk, he was talking more about the logarithmic case, but even there, he, at least with reconstruction, at 1, you were still not being able to see the oscillatory features anymore. It seems, maybe 0.5-ish is still possible, but yeah, we. Yeah, much it. Mm-hmm. Yeah, we're trying to do it. It's just that, we had never used Cobaya before ACT came out and we're just having a little technical troubles doing the frequentist analysis. If anyone has, input, I would love to hear it. Yes, like, uh, mhm. I think, going a little bit higher, you probably still gain, and but yeah, I don't know to what extent. I mean, it's something we're still kind of. I mean, we just started thinking, so I don't know, because I think the normal cut is more like 0.2-ish, 0.1, 0.2-ish. So if you go to 0.5, you in principle can still gain a lot. But yeah. Uh-huh. I mean, oh yeah, we didn't put in the. I mean, it depends. I mean, you can move it to a little bit higher, and then I can still probably get it few percent. But I think if you want to put it right at 0.1, you're probably getting it. I mean, it's more ineffective that constraining than the fraction of interacting dark matter, really. No, I mean, if you want to get large and effective, then you normally have to put some amount of interacting dark matter, because that's what buying you that freedom, right? But if you're putting a little, then you don't care as much. But of course, if you put too little, then you don't have any pressure, so then you don't have the feature either. But I think if you're around 0.1, you probably still have some freedom. I mean, we need to look. I haven't looked super carefully, but I feel like if you're near 0.1, you're probably still fine.